Hello, chemists. This is Miss Placino, and you are watching Screamcast 8.4 on Half-Life. Today we're going to switch gears from what we've been talking about so far with nuclear chemistry. We've looked at natural transmutations, artificial transmutations, fission, fusion. We've talked about writing and consequently balancing decay equations. Half-Life is a different beast altogether. Half-Life is looking at the rate that these decays are occurring. So the math is going to be a little bit more complicated than what we've talked about so far. So you're probably going to want to make sure that you have a calculator with you as we're walking through some practice problems. All right, hopefully by this point in time, we're pretty comfortable with the idea of nuclear decay. You've got a nucleus that is unstable due to an unfavorable proton to neutron ratio, and the nucleus undergoes alpha, beta, positron, gamma, electron capture, something to try to stabilize the nucleus. What Half-Life is looking at is how much time it's going to take for half of the atoms in a radioactive sample to decay. Eventually, virtually all of them will decay. Half-Life wants to look at, or is looking at, how long does it take for half of them to decay? Scientists are interested in half-life for a variety of reasons. One reason is the half-life of radioisotopes is constant. Unlike chemical reactions and chemical changes where different environmental factors, something like temperature or pressure, for example, can change the rate of the reaction, there is no way to change the rate of radioactive decay. The half-life of a radioisotope is an intrinsic property that cannot be altered. So scientists are able to use things like half-life to figure out the age of the Earth, to figure out the age of ancient remains, all because it doesn't matter what's happening in the external world, half-life remains constant. So we're going to use table N to find the half-life of different radioisotopes. So we've used this table before. It's a really important table for the nuclear chemistry unit. In previous lessons, we were focusing on decay mode, so we could know whether a specific radioisotope underwent alpha, beta, gamma, or positron decay. Today, as you might imagine, we're concerned with half-life. Half-life, again, is the amount of time it takes for 1/2 of the atoms in a radioactive sample to decay. So half-life is going to be measured in time. If you look, the units are different. So sometimes they're as short as milliseconds. Sometimes units are as long as years. So be careful when you're doing any problems with half-life. Really make sure that in addition to finding the correct radioisotope, which can be tricky, that you are looking and paying attention to the unit. You'll see that not all radioisotopes have the same half-life. They all have different half-lives. Something like gold-198, yes, there is a radioactive form of gold, decays with a half-life of 2.69 days. Something like carbon-14 has a half-life of 5,730 years. Based on the time of half-life, you can make some conclusions about the stability of that radioisotope. It turns out that the longer the half-life is, the more stable that radioisotope is. So carbon-14 atoms take a very long time for half of the atoms in a radioactive sample to decay, whereas something like gold-198 or even less stable, calcium-37, they're going to decay much more quickly, which would lead one to believe that their nucleus is less stable. But regardless of whether you have a long half-life or a short half-life, what nuclide you're looking at, half-life always follows the same pattern. So on the x-axis, we have number of half-lives. On the y-axis, we have percent of the sample remaining. So what percent of the atoms in our radioactive sample are still radioactive? If it's a little bit difficult to think about percent, you can think about this as being just atoms remaining. So you think about before any half-lives have elapsed, we have 100 atoms. After one half-life, whether we're talking about 10 milliseconds or 10,000 years, half of the atoms decay. So 50% decay, half of 100. Again, if we want to think about it in terms of atoms, that would leave me with 50 atoms. Again, it does not matter how long the half-life is or what radioisotope in particular you're looking at. They all follow this pattern. If another half-life elapsed, I lose 50% of my 50 atoms remaining, so I'd be left with 25% of my sample. Or if I started with a 100-atom sample, I have 25 atoms remaining. I can undergo another half-life, and 50% of my now 25 or 25 atoms remaining will decay. Hopefully we recognize that we can't have like a 0.5 if we're talking about atoms, but if we're looking at just relative percentages, of course you can. So every single time you undergo one half-life, half of the atoms decay, and we get down to smaller and smaller quantities of our radioactive sample. For those of you who have seen these type of graphs before, you know it's impossible to get to zero from a mathematical perspective. So usually scientists will deem after 10 half-lives a sample is no longer radioactive. It's undergone so many half-lives and has decreased by so much that for all practical intents and purposes, it is no longer radioactive. Let's do some practice problems with half-life. So I'm going to pull that up right now. All right, so we've got about 10 different practice problems, and don't panic, we won't go through all of them. I just want to talk about a couple of them and give you some techniques to figure out these types of problems. There are some, let's say, more mathematically elegant ways to solve half-life. I'm not going to talk about them here. I'm going to use a technique that my chemistry teacher when I was in high school called brute force and ignorance. So it's not going to be fancy, it's not going to be pretty, but it will yield the correct answer with pretty minimal math skills required. Okay, question number 1. The half-life of zinc 71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes have elapsed? Okay, so we know the half-life of zinc 71. We're told it's 2.4 minutes. We know how much total time has passed, 7.2 minutes. And we know, sorry about that, how much we're starting with. And a lot of times with half-life problems, you're going to be given a mass in grams. The first thing I want to figure out is how many half-lives have elapsed. So I know how much time has passed, and I know how much time a half-life is. So I can figure that out pretty quickly. I waited 7.2 minutes. Half-life happens every 2.4 minutes. So I'm going to end up with, careful with my math, 3 half-lives. And I'm just going to abbreviate half-life with HL. So I know that 3 half-lives have passed. So my 100-gram sample has been cut in half 3 different times. The way I like to show this is I'll start off with my 100 grams. And a half-life cuts everything in half, so I'm just going to divide by 2. I put an arrow. 100 divided by 2, that's math I can handle, is 50 grams. Well, that's 1 half-life. Let's go through a second. I'll divide that by 2 again. I get 25.0 grams. 1 half-life, 2 half-lives. Let's divide by 2 one more time to get to 3 half-lives. And I've got 12.5 grams. With half-life problems, please don't stress over significant figures. I'm not going to be too worried about them. I just really want to see that you can do the work. So what we see is really every time you draw an arrow like this, you've gone through a half-life. So I've got 1, 2, 3 half-lives that have elapsed. I calculated based on the information provided that 3 half-lives have passed. So if I start with 100 grams, after 7.2 minutes, I should have 12.5 grams of zinc 71 remaining. That's basically how you want to try to solve these problems. Figure out how many half-lives have gone by, and then what impact is that going to have on the total amount of sample that you have. I want to skip down and look at question number 4. So we're told after 24 days, 2 milligrams of an original 128 milligram sample remain. What is the half-life of this sample? So in this case, we're trying to figure out how long it takes one half-life to elapse. So I know the total amount of time, 24 days. I know how much of my radioactive sample I currently have, 2 milligrams. I know what I started with, 128 milligrams. Okay, so in this case, I need to figure out how many times the sample was cut in half. In other words, I need to figure out how many half-lives have elapsed. I'm going to do this very, not elegantly from a mathematical perspective. I know I started off with 128.0 milligrams. And what I'm going to do is just divide by 2 until I get down to the 2 milligrams that I am currently left with. And I'm not going to be too concerned with my significant figures. Truth be told, I'm not too concerned with units right now. I'm just concerned with dividing by 2 again and again and again until I get down to, in this case, my 2 milligram sample. And here I am. I'm going to count my arrows because that's going to tell me how many half-lives have elapsed. I've got 1, 2, 3, 4, 5, 6. So I've undergone 6 half-lives. H.L. So I know 6 half-lives have passed and a total of 24 days have elapsed. So I'm trying to figure out what the length of the half-life is for a sample. So I'm guessing you probably know how to do this, but just to make sure we're all on the same page, I've got 24 days. I've undergone 6 half-lives. Hopefully the math here is not too complicated. That gives me 4 days per half-life. And that's it. This technique of just dividing by 2 is going to work pretty much every single time as long as you're careful with your math. I know I've alluded to it a couple of times now, but some of your classmates might be able to do this in a more mathematically elegant way. If you don't feel comfortable doing that, there is no shame in dividing by 2 repeatedly. I will admit it, this is the way I tend to do it myself, especially because you don't really need to get into like exponential relationships to solve the type of questions we're going to see here. It's going to work out that we're always going to end up with a whole number of half-lives. So in other words, I can give you 3 half-lives, I can give you 6 half-lives, I can't give you 5.73 half-lives. That just kind of makes things more complicated than they need to be at this point in time. So brute force and ignorance, aka dividing by 2 until you get to the final answer, is going to work out just fine. Okay, I'm going to leave you with those questions and practice problems to work on your own. Be careful with the math. Make sure that you are reading the question carefully and that you are answering the question that is being answered. A lot of people tend to rush through and just kind of make some careless mistakes. That's all I've got for today. Thank you for tuning in, and I hope you found this helpful.